We have already studied the motion of a body under the influence of gravity in the case of free fall. Now we present a similar type of motion, the motion of projectiles. Projectile motion is the motion of a body thrown or projected into the air under the influence of gravity. The body undergoing such a motion is called projectile. Let us consider some examples for projectile motion. The first one is the simplest example, the motion of a stone thrown by hand. If we throw a stone away, then it will only be subject to acceleration as a result of gravity. The next example is the moving projectile of a cannon, which is one of the most effective apparatus to launch projectiles. Typical long-range cannons can reach targets within a couple of 100 kilometers. As opposed to cannons, where the long horizontal range of the projectile is an important factor, firework projectiles are launched to higher altitudes, where they explode away, and the portions of the shell fall back to the ground as burning debris. Another typical example for the phenomenon of projectile motion is a water fountain, where the stream of water follows the trajectory of the projected water. In many cases, we also need to take into account the fact that the air resistance modifies the trajectory of the projectile. Since the resistance of the air depends on the shape of the projectile, different projectiles launched with the same thrust in the same direction will cover different trajectories. Therefore, the air resistance makes the motion more complicated, and it is practical to neglect it in the study of the basic motion of the projectile. Then the motion is completely determined by the gravitational acceleration. The air resistance is completely eliminated if we study the projectile motion in vacuum. However, such experiments can only be performed in vacuum chambers, which are not always available. A simpler solution is a suitable choice of the projectile, so that we could mitigate the effect of the air resistance on the motion. If the size of the projectile is negligible, then the air drag acting on the moving body can be reduced. At the same time, the heavier the projectile is, the smaller the effect due to the air resistance will become. That is, in the case of small but heavy projectiles we can neglect the air resistance if the launched objects do not move too fast. Then we apply an idealized model for the projectile, and we regard it as a point mass in the study of its motion. Let us start the discussion with horizontally launched projectiles. The following experiment helps us to understand what happens if we launch a projectile in the horizontal direction. In the experimental setup, a flexible metal plate fixed at its upper edge presses the ball A to a slab, and holds it in a fixed position in the left-hand side of the plate. In the right-hand side of the plate the ball B rests on a ramp. A hammer is suspended in the left-hand side of the plate. This apparatus is placed at a given height above the floor. If we release the hammer, it will strike the plate, which will bend, releasing the ball A, and pushing the ball B left to right in the horizontal direction. As a result, we let the ball A fall down and we launch the ball B horizontally in the right direction at the same time. By performing this experiment, we can demonstrate that the falling and the projected balls will hit the floor in the same time. In order to describe the motion of the balls, we choose the ramp as the reference point O, and attach a two-dimensional Cartesian coordinate system to it. The x-axis of the coordinate system points in the left direction, and the z-axis points downwards. If we choose the equidistant points x1, x2, and x3 along the x-axis, and project them onto the trajectory of the projectile, then we obtain the points p1, p2, and p3. By measuring the vertical coordinate z1, z2, and z3 of these points, we find the following relations between the equidistant x-coordinates and the z-coordinates. By definition, the ratios between the equidistant coordinates are given by the ratios 1, 2, and 3. For the vertical coordinates z1, z2, and z3 we measure the ratios 1, 4, and 9. We can perform this measurement by mounting rings in the positions p1, p2, and p3 on a wall parallel with the xz plane. If the planes of the rings are perpendicular to the direction of the motion of the ball B in the corresponding points, then the projectile can pass through the rings in each point. This result demonstrates that the ratios stated above hold between the vertical and the horizontal coordinates of the trajectory of the projectile. Since the ball A falls freely, its vertical coordinate z is given by the gravitational acceleration g times the square of the time t divided by 2. Let us consider the moments at the time t1, t2, and t3, when the ball A passes the points z1, z2, and z3 along the z-axis. We can determine the relations between t1, t2, and t3 and the coordinates z1, z2, and z3, by applying the equation of motion for freefall. As a result, the ratios between z1, z2, and z3 are equal to the ratios between t1 squared, t2 squared, and t3 squared. Since the two balls hit the floor at the same time, the ball B needs the same time intervals to cover its path between the points O and P1, O and P2, and O and P3. But we have already seen that the ratios between the coordinates Z1, Z2, and Z3 are given by 1, 4, and 9. That is, the ratios between T1 squared, T2 squared, and T3 squared are equal to the ratios between 1, 4, and 9. This means that the ratios between T1, T2, and T3 are equal to the ratios between 1, 2, and 3. As we have stated, the ball B covers the paths between the points O and P1, O and P2, and O and P3 during these time intervals. That is, it covers the vertical distances x1, x2, and x3 during the intervals T1, T2, and T3 respectively. Since the ratios between these time intervals are the same as those of the equidistant coordinates x1, x2, and x3, we can conclude that the vertical distance x covered by the ball B is directly proportional to the elapsed time t. Then we have demonstrated that the motion of a horizontally launched projectile is the composition of a uniform motion along a horizontal line and a vertical free fall. That is, its equations of motion are the following. In the vertical direction, the distance x covered by the projectile is equal to v0 times the time t, where v0 is the initial velocity of the projectile. In the horizontal direction, the distance z covered by the projectile is given by the gravitational acceleration g times the square of the time t divided by 2. If we eliminate the time t from these two equations and solve the result for the coordinate z, then we obtain that the coordinate z is equal to g over 2 times v0 squared times x squared. This is an equation of a parabola located in the xz plane, that is, the path of the projectile is a parabola lying in the vertical plane oriented the direction of the launch. In the general case of projectile motion, the projectile is launched in an arbitrary direction. Let us suppose that the projectile is launched with the initial velocity v0. That is, the speed and the direction of the launch is determined by the vector v0, where alpha is the angle between the direction of the vector and the horizontal direction. The launched body moves in the vertical plane of v0, and we choose it as the plane of the two-dimensional Cartesian coordinate system. We pick the point of the launch as the reference point O, and we attach the coordinate axes to it, so that the x-axis points in the horizontal direction and the z-axis points upwards. The initial condition for the projectile t equal to 0 is the following. The x and z coordinates of the projectile are 0, and the x and z component of its initial velocity are given by v0 times cosine alpha and v0 times sine alpha, respectively. By generalizing the results of the experiment with the horizontally launched projectile, we claim that the motion is the composition of a uniform linear motion in the direction of the vector v0, and the free fall of the projectile. We can describe the uniform linear motion of the body passing through the equidistant points A1, A2, A3 without free fall in the following table. In the first row, we will show the time elapsed till the projectile would reach any of these points if it had a uniform linear motion in the direction of v0. In the second row, we will write the distances covered during the time intervals given in the first row. The time t1, when the body passes through the point A1, is given by a time interval delta t, which depends on the velocity v0. The distance vector between the points O and A1 is equal to v0 times delta t. At the time t2, the body passes through the point A2. Since we talk about a uniform linear motion, t2 is given by 2 times delta t. Then the distance vector between the points O and A2 is equal to 2 times v0 times delta t. The time t3, at which the body passes through the point A3, is given by 3 times delta t, and the distance vector between the points O and A3 is equal to 3 times v0 times delta t. We could continue this process with further points on the path of the uniform linear motion. The next table shows the covered distances of the body in the case of free fall started from the points A1, A2, and A3 for the same sequence of time. If the body fell freely from the point A1, then it would travel a distance g times delta t squared divided by 2 during the time 1t. Let p1 denote the point with this vertical distance from the point A1, and let s1 denote the distance between A1 and p1. At the time t2, the body freely falling from the point A2 would cover the distance g times the square of 2 times delta t divided by 2. Then the distance between the point A2 and p2 would be given by 4 times s1. If the body fell freely from the point A3, then the distance traveled by the body during the time t3 would be equal to g times the square of 3 times delta t divided by 2. As a result, the distance between the point A3 and p3 is given by 9 times s1. We could continue this table with a sequence of distance-time relations for free fall. Now we are able to construct the series of the points P1, P2 and P3 from the composition of the uniform linear motion and the free fall of the projectile. If we translate the vertical distance A1 P1 to the head of the vector OA1, then we obtain the position P1 of projectile at the time T1. Similarly, the translation of the vertical distance A2 P2 to the head of the vector OA2 gives the position P2 of the body at the time T2. The position P3 of the projectile at the time T3 is determined by translating the vertical distance A3 P3 to the head of the vector OA3. In general, if the projectile is in the point P at the time T, then the x-component of the position vector OP are given by the distance OA times cosine alpha, and its z-component is equal to OA times sine alpha, minus 1 over 2 times g times t squared. Here the length of the position vector OA is simply v0 times the time t. This general case shows that the trajectory of the projectile is a parabola with a vertical axis. Then we conclude that the equations of motion for the projectile launched with the initial velocity v0 are the following. The x-component of its position vector is given by the magnitude of v0 times the time t times cosine alpha. And its c-component is equal to the magnitude of v0 times the time t times sine alpha, minus 1 over 2 times the gravitational acceleration g times the square of the time t. Now we formulate the composition principle used to determine the displacement of a projectile launched in an arbitrary direction, and we also elaborate its equations of motion. The motion of a projectile launched with the initial velocity v0 is the composition of a linear uniform motion in the direction of v0 and the free fall of the projectile. The equations of motion for the projectile are the following. The displacement of the projectile in the horizontal direction is along the x-axis and is given by the magnitude v0 of the initial velocity times the time t, times cosine of the inclination angle alpha of the launch. The vertical displacement z is equal to the magnitude of v0 times the time t times sine alpha, minus 1 over 2 times the gravitational acceleration g times t squared. Here we see that the horizontal displacement is due to the uniform linear motion, whereas the vertical displacement is the composition of the uniform linear motion and the free fall of the projectile. The derivatives of these equations with respect to the time t give the components of the velocity of the projectile. The x-component of the velocity is given by v0 times cosine alpha, and its c-component is equal to v0 times sine alpha, minus g times t. In the horizontal direction, we have the horizontal component of the initial velocity vector v0. In the vertical direction, we have both the vertical component of the initial velocity and the instantaneous velocity due to the free fall of the projectile. The derivatives of the velocity components of the projectile with respect to the time provide the component of its acceleration. The horizontal component of the acceleration vanishes, since we have only the uniform linear motion in the x direction, while its vertical component is equal to minus the gravitational acceleration g. The minus sign indicates that the z-axis and the gravitational acceleration vector point in the opposite directions. If we eliminate the time t from the component equations of the displacement, we can determine the vertical coordinate z as a function of the horizontal coordinate x. This gives the equation of the projectile's trajectory, which states that z is equal to x times tangent alpha, minus g over 2 times v0 squared times the square of cosine alpha, times x squared. The trajectory equation holds, provided the angle alpha of the launch is not equal to the right angle, that is, the projectile is not launched vertically. As we have already stated, this is an equation of a parabolic trajectory with a vertical axis. This axis determines the maximum height of the parabola. Since at the maximum height of its parabolic trajectory the vertical velocity of the projectile vanishes, we can determine the time required to reach the maximum height h from the equation of the z-component of the velocity. If vz vanishes at a given time th, then v0 times sine alpha minus g times th is equal to 0. As a result, we can solve this equation for the time, and we obtain that th is given by the ratio of v0 times sine alpha to g. Now we can substitute the time th into the equation of the trajectory. Then the maximum height h, which is the vertical coordinate z measured at the time t, is equal to v0 times the ratio of v0 times sine alpha to g, times sine alpha, minus 1 over 2 times g times the square of the ratio of v0 times sine alpha to g. This gives v0 squared times the square of sine alpha, divided by 2 times g. Then we see that the greater the initial velocity v0 and the inclination angle alpha of the launch are, the higher the maximum height h of the trajectory of the projectile is. We can also determine other special quantities which characterize the trajectory of the projectile, such as the total time, the range and the maximum distance of the flight. When the projectile hits the ground, its vertical coordinate z vanishes. Then we can apply the equation of the vertical displacement z to determine the total time t-tot of the flight of the projectile. The coordinate z measured at the time t-tot vanishes, that is v0 times t-tot times sine alpha, minus 1 over 2 times g times t-tot squared is equal to 0. We can solve this equation for t-tot, which gives 2 times v0 times sine alpha, divided by g. This is 2 times the time th needed to reach the maximal height, since the parabolic trajectory is symmetric to the vertical axis at its maximum height. If we substitute the total flight time t-tot into the equation of the horizontal coordinate x, we obtain the range of the projectile. The horizontal displacement x measured at the time t-tot is given by 2 times v0 squared times sine alpha divided by g, times cosine alpha, which is equal to v0 squared times sine 2 alpha, divided by g. From this result we determine the maximum distance which can be reached by the projectile. For a given magnitude of the initial velocity v0, the projectile reaches the maximum distance if sine 2 alpha is maximal, that is, if sine 2 alpha is equal to 1. Then the angle alpha of the launch must be 45 degrees. In that case, the maximal distance is given by the ratio of v0 squared to g. If the angle of the launch is greater or smaller than 45 degrees, the range of the projectile will be smaller than the maximal distance for a given speed v0 of the launch. We can launch the projectile with a flat trajectory, that is with an inclination angle alpha 1 less than 45 degree, or with steep trajectory under the angle alpha 2 equal to 90 degrees minus alpha 1. Then the range of the projectile is the same for both the flat and the steep trajectories, since sine 2 times alpha 2 is equal to the sine of 180 degrees minus 2 times alpha 1, which is simply sine 2 times alpha 1. That is, the range x of the projectile measured at time t-tot is the same for both the ratio v0 squared times sine 2 times alpha 1 to g, and the ratio v0 squared times sine 2 times alpha 2 to g. Thus, we found a pair of trajectories, a flat trajectory and a steep one covering the same range. Let us summarize the equations of motion for projectile motion, and see how we can obtain the equations for the horizontally and vertically launched projectiles as special cases of the projectiles launched in an arbitrary direction. We start with the general case, where the initial velocity of the projectile is equal to v0, and alpha is the angle between the direction of the initial velocity vector and the horizontal direction. One of special cases is the horizontally launched projectile, where the inclination angle alpha of the launch is equal to 0. The other special case we consider here is the vertically launched projectile, where alpha is equal to 90 degrees. In the general case, the displacement of the projectile measured from the position of its launch at the duration t is given by the following equations. The horizontal displacement x is completely determined by the horizontal component of the initial velocity, and it is equal to v0 times t times cosine alpha. The vertical displacement z is determined by both the initial velocity vector v0 and the free fall of the projectile, and it is given by v0 times t times sine alpha, minus 1 over 2 times the gravitational acceleration g times t squared. In the case of the horizontally launched projectile, cosine alpha is equal to 1 and sine alpha vanishes. Then the displacement x is given by v0 times t, and the equation of the displacement z reduces to minus 1 over 2 times g times t squared. In the case of the vertically launched projectile, cosine alpha vanishes and sine alpha is equal to 1. As a result, the horizontal displacement x of the projectile is 0, as it must be for a vertically launched body, and the vertical displacement z is equal to v0 times t, minus 1 over 2 times g times t squared. The velocity of the projectile in the general case is the following. Its horizontal component vx is given by v0 times cosine alpha, and its vertical component vz is equal to v0 times sine alpha minus g times t. In the case of the horizontally launched projectile, the horizontal component of the velocity is simply the initial velocity v0, whereas the vertical component vz is given by minus g times t. In the case of the vertically launched projectile, there is no horizontal component of the velocity, that is vx vanishes, and its vertical component vz is equal to the initial velocity v0 minus g times t. The acceleration of the projectile in the general case is very simple. There is no horizontal component of the acceleration, that is x vanishes, and the vertical component az is minus g, that is the gravitational acceleration pointing downwards. Since the acceleration of the projectile does not depend on the inclination angle alpha of its launch, the acceleration is the same in both the special cases, that is for the horizontally launched projectile and the vertically launched one. In the general case, the trajectory of the projectile is given by the vertical coordinate z as a function of the horizontal coordinate x, which states that the coordinate z is equal to x times tangent alpha, minus g over 2 times v0 squared times the square of cosine alpha, times x squared. In the case of the horizontal projection, the trajectory equation reduces to z equal to minus g divided by 2 times v0 squared, times x squared. In the case of the vertical projection, this equation is not applicable, since the vertical coordinate z is not a unique function of the horizontal coordinate x, which remains 0 during the motion. We also determine the maximum height h, which can be reached by the projectile in the general case, and it is given by v0 squared times the square of sine alpha divided by 2 times g. The duration th for this distance is equal to v0 times sine alpha over g. This is not applicable for the horizontal projection, since the maximum height of the falling projectile is the point x equal to 0, which is the point of the launch. In the case of the vertically launched projectile, the maximal height h is given by v0 squared over 2 times g, and the duration th is equal to v0 divided by g. In the general case, the maximum range covered by the projectile is equal to v0 squared times the sine of 2 times alpha divided by g. The total time measured until the projectile falls back on the ground is just 2 times the duration th. These formulae cannot be applied for the special cases, since in the case of the horizontally launched projectile, the vertical position always remains under the latitude of the launch at z equal to 0, and in the case of the vertical launch, the projectile always moves along the vertical z-axis.